Hello, everyone. Welcome to the AI Agents Hackathon live streams.
The AI Agents Hackathon is a free virtual hackathon running from April 8th to April 30th.
We're hosting over 20 live streams where you'll learn how to build agents using various Microsoft technologies. At the end of the 3 weeks, submit your project for a chance to win fantastic prizes.
And now over to our friends at Reactor.
Hi, everyone. Thanks for joining us for the AI Agent Hack. Before we start, I do have some quick housekeeping. Please take a moment to review our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is recorded. It will be available to view on demand within 24 to 48 hours. With that, I'd love to turn it over to our speakers for today. Thanks for joining.
Hello, everybody, and welcome to this session about engineering agents that think, act, and govern themselves. The session will dive into the design and operational concerns of autonomous AI agents and explore how they can act responsible, self-improve, and remain controllable. With me, I have Henry.
Hello. Hi, my name is Henry. I work as an AI solutions architect at Microsoft here in Denmark, and I've got the pleasure of sitting here today with Thomas.
Yes. And my name is Thomas Martinsen. I work as a technical evangelist at Today, and also have the pleasure of being a Microsoft Regional Director and AI MVP. So for the session today, we are going to take you through a few different steps. First, we're going to look at some reflection, how we build agents that can reflect on actions and how they reason based on that. Then we will take a look at some different strategies. We'll look at selection and termination in multi-agent solutions. It's really important to have a strategy for whose turn it is to talk and also when a result is good enough to stop. Then we'll take a look at some scaling of agents. When do we need to split some of the actions into multiple agents? And after that, we'll take a look at how we handle memory. So how do agents use memory to improve their dialogue and their actions? And in the end, we will have a Q&A. So don't hesitate to write questions in the chat or comments area.
That's right. All right, now you've got a little bit of an idea of what to expect from the session. There's a few other things we should maybe highlight, right?
Yep.
First of all, you've seen we're not doing any slides today, so everything is just kind of a whiteboard, plus a bunch of live demos that we're quite excited about. You'll be seeing us live demo things in both Python and C#. So no matter what your preferred programming language is, you will find this relevant, I hope. Everything that we're doing here today can be done in both languages. So it doesn't matter which one we're demoing in Python, which one we're demoing in C#. They are pretty much interchangeable in that way. They'll just look a little different, right? What else to expect? We will, of course, take you through these little topics, and then usually we will also introduce you to a matching, you could say, multi-agency strategy or multi-agency framework along the line as well. So stay tuned for those as well. Good. Before we get properly started, we should mention a few things that we hope you've already come across during previous sessions here of the hackathon, or maybe you've been working with this already. But we assume everybody by now has a basic understanding of what AI agents are, how you can have basic agents from very, very simple retrieval agents to agents that perform operations, what we call task agents, or more autonomous agents that potentially operate without any actual human input or direct trigger. Now, we also assume, given that this is a hackathon, that you have built an agent before. I mean, you've been probably working on an agent or some agent system for the past couple of weeks already. So you probably know the components of agents as well. You know that we're building agents on top of foundation models, large language models, small language models as well in many cases. And then we tag on agentic capabilities by adding knowledge, by adding skills, or by adding components that provide autonomy. All of this powered by and made possible by some kind of orchestrator. And you probably also know that one agent can work together with other agents, that we can orchestrate agents into multi-agent systems. And one of the frameworks that we're going to be using to do that, and that you might have also come across, is semantic kernel. And we're using semantic kernel for a number of reasons. For one, it's a good stable framework that we can actually use for orchestrating multi-agents. It allows us to connect our code with the AI models, whether we're using models from OpenAI or whether we're using other type of vendors. And it allows us to bring in our own plugins and our own data with a lot of different connectors. The other thing is, Thomas likes to write in C#, and I like to write in Python. And even if we had a third person here that liked to write in Java, we would all be able to do that with semantic kernel. So that's the other nice thing and the other reason for why we've chosen to demo semantic kernel or show you our demos with semantic kernel today. Good. Are we ready to get started?
Yeah, I think so.
Awesome. Great. Then let me just find the first part here. We wanted to get started with reflection, with the first part of agents. So we named it agents that think, act, and govern themselves. So we wanted to start, at the think part, you could say the simplest part, and that is, how do we actually make agents that think effectively? Because here's the thing. When large language models started being used in chatbots, let's say take a simple chatbot like ChatGPT or Copilot, and people started using it, they slowly started finding out how large language models actually work and how they generate tokens. Many of you are probably familiar with the kind of stochastic behavior and how tokens are generated. And you will know that large language models, they tend to just generate tokens. Most traditional large language models now they generate tokens unidirectionally, right? They only generate tokens in one direction, that is forward. So when I have a sentence like, when the sun is out, Henry goes to the blank, a large language model will put in a token or a word here that seems to make sense with the context that comes before it. Obviously, the model doesn't know yet what it will be generating after, so it can't consider what comes afterwards. But now, some words are going to be more useful here than others. If we take park, for example, I live in Denmark. When the sun is out in Denmark, it's nice outside. For once, it's the only time when it's nice outside is when the sun is out. So I might want to go to the park. That's a good suggestion. That would be a pretty good token to suggest here. But maybe it would suggest Henry goes to the dump. That's a pretty bad suggestion, regardless of weather, actually. Or maybe the mall, the library. There's lots of places where I wouldn't necessarily go when the sun is out. I might want to be outdoors rather than indoors. So, of course, we have no problem, or large language models have no problem understanding that if they generate a token here that doesn't actually fit, because it's just unlikely, but the chance is not zero, they have no problem detecting that and fixing that if we give them a chance. So, of course, one thing we can do with large language models is we can ask them to reflect. But usually we don't want to have to do that. We don't want to have to ask for our outputs to be good, right? Especially when we talk about autonomous agents, we need our outputs to be good by default, by design, right? So what can we do? One of the things that you might have seen get more and more popular is reasoning models. And this is not a talk or not a session about reasoning models, but I want to quickly show you this example because it drives home a particular point that I want to make. Let's quickly jump into the GitHub model catalog. In here, we can try out all kinds of different models. And for now, let's I've selected here the DeepSeek R1 reasoning model. You can see there's all kinds of different models in here. But I wanted to quickly show you a reasoning model for one very particular reason. That is, if I ask a simple question, like, for example, what is 1 + 1? Right? Very, very basic question. What this allows us to do is to look inside of the reasoning of this model. So we can actually see here, it uses this think tag to differentiate the reasoning from the actual output. And we can see it says, okay, we need to figure out what 1 + 1 is. Let's start by recalling basic addition and so on and so forth. And it works itself through this process. It says, oh, this is interesting. In binary, 1 + 1 would be 1, 0, where usually it equals 2. So it's thinking about this from different perspectives. And then ultimately, it gives us an answer. The sum of 1 and 1 is 2. But you might find that when you're doing something like this, these reasoning models, they look at a lot of different directions, right? They look at, like I mentioned, binary. That could be one thing. They say in this example, I tried this earlier, and it said, oh, maybe this is a setup for a joke, right? Maybe this is a child that's learning math, so I should take this very literal, or all kinds of different reasons for why the user might have asked this question, and what kind of answer they might then be expecting in return. And this is the kind of behavior we want from our agents. We want our agents to reflect rather than just flat out giving us an answer. And this is where, this is, I suppose, one reason why we can now, build agents on reasoning models. But there's another way to make that work as well. And this is where I want to introduce you to the first pattern of multi-agency here, and arguably a very basic pattern, but a very useful pattern. And most of you who are working with multi-agency, this is probably the pattern that you started working with because it is so very, very useful. It helps us to create reflection, helps us to reflect. And in this pattern, we use two agents, one worker that executes some kind of task, and one reviewer that makes sure that that task is actually properly executed. And I want to show you what this can look like with a little demo. So what I have set up, and you can find, by the way, we'll be sharing the code to all of these demos as well in the chat. What I've set up is a very, very, very simple. I've actually, this is mostly just from the semantic kernel samples repository, but I've mostly set up a very simple multi-agent setup here in Python that utilizes two agents. Remember, we have one worker and one reviewer. In our case here, we've got a math professor, and I've prompted the math professor to, to figure out a math problem and to discuss with the colleagues, and ultimately then to say, that the problem is solved when the problem is solved. Let me just make that just a tiny tad bigger for you. So this is our reviewer. But then we also have another agent here. And this agent is there to provide a different perspective. So in this case here, I've named it the computer science professor. And this agent has been prompted to prefer operations in binary, just to provide a different perspective. And then we are giving it a task. This is where, in a chat application, the user might be providing an input. In an automated application, this might be what's coming in from some kind of trigger. In our task, this is very, very simple. We're setting up the agents. I'm using Azure AI Agent Service, by the way. It makes this relatively simple. I'm just providing the name that I've defined earlier, the instructions, and then actually creating, in this case, an Azure AI agent. If I wanted to, I could also do this with the thread completion API. I could do this with the response API. I could do this with the OpenAI API also. There's lots of different ways that we can create agents that behave very similarly to this. Now, I'm doing this once, but I'm also doing this twice just to set up the second agent as well. The interesting part is down here when we're then actually creating a group chat. And this is semantic kernel's way of saying we are putting these two individual agents into a group, and then we're just letting them talk with one another. This is where our reflection pattern comes about. And we could invoke these agents individually. Absolutely, we could do that if we just wanted to talk to an individual agent. But this group chat allows us to actually, talk to a group of agents. You can see here I'm defining the agents as a list, but I want to show you quickly what happens if we actually just run this with a single agent. And this would just be the math professor alone. So I'm just running this here directly in VS Code for simplicity's sake. And you will see that the first thing that will happen once it starts up is that we can see the task here coming from our user. There you go. And then we should see the agents starting to discuss. Now, remember, in our example right now, the way we've configured it, there's only one agent. It's only the math professor. So let's have a look what he says here. The math professor says the answer is 2. As simple as that. The sum of 1 and 1 results in 2. What say you, colleague? There's no colleague. And then the math professor answers itself and says, your conclusion is correct. It's definitely 2. I declare this problem solved. So very nice, but a little one-sided, right?
I really like the tone of the professor here, right?
And this
Old
is
English.
Somewhat accidental because I prompted the professor to be an old school math professor.
Yeah.
My idea with this was originally to say, I don't want the math professor to think about binary notation.
Mm-hmm.
But it turned out that this is what came out, and I love it, so I just stuck with it. All right, okay. So this was just this was a very, very boring, arguably a boring demo. Let us add the binary agent back into the equation, or rather back into the group chat, and run this again. And this time what we should be able to see is agents actually discussing with one another, disagreeing, reflecting. Now, to be fair, a question like 1 + 1 is not that difficult. There isn't that much reflecting to be done here, but there is one critical element of reflection that we're hoping to see here. So the math professor starts it up again here, a classic arithmetic problem. The sum of 1 + 1 is 2. Do you have any additional thought? And the computer science professor says, oh, well, but switching to binary, 1 + 1 is 1, 0. So now we see the same behavior here that we saw with our reasoning model. And the math professor agrees and says, well, I see your approach. In binary, you're absolutely right. And then ultimately says a fine conclusion. In decimal, it's 2. In binary, it's 1, 0. Both are correct in their respective systems. I declare this problem solved. So suddenly, by just adding a second agent into this conversation, we've been able to simulate this, or not simulate, but actually to force the agents to take different positions and to reflect. And this leads us to a solution that is arguably or inarguably more complete. Mm-hmm. It's just a better solution, right?
Yep.
We don't just get the answer in decimal, but also in binary. So, and this is arguably a silly example. I really like the word arguably today. This is a very silly example, but think about how many other areas you could apply this to, where you might have people with different expertise that need to take different perspectives on a problem and provide their input in order to arrive at a complete solution. So that was just a tiny little bit on reflection. But due to time, we gotta move on because there's more demos to come. And I want us to focus on one particular thing. And that is, how did these demos actually stop? And you can see already here in the prompt, I said, if you have considered your colleague's feedback, summarize the combined solution and state the following phrase: I declare this problem solved. Now, this doesn't, by itself, doesn't do anything automatically. There is no inherent magic in semantic kernel that determines when these agents might be done. Instead, I have defined a termination strategy here. And what I've done here is that I have said, when we get a message back, let's check if that message is terminating the conversation. In this case here, I am looking for the string, I declare this problem solved. It's a very low-tech approach, right? But it is the easiest way we can, or one of the easiest ways we can actually solve this. Let me quickly show you where we are implementing that. That's down here somewhere, where when I'm setting up the group chat, I'm not just defining the agents. By the way, the order matters here. This is the order in which they go. But I'm also defining my termination strategy. And I'm defining here which of these agents this termination strategy actually applies to. Since I'm doing this reflection architecture, where one is a reviewer and one is a worker, I'm only applying this to the reviewer agent. And then I'm saying, look, but if you don't finish within 10 turns, we're going to cut you off, because then probably you're never going to finish, right? With a simple task like this. But let me show you, I'm just quickly going to jump over to another demo here. What happens if we are applying this termination strategy across all of our agents? So I've changed the setup a tiny little bit here, and I've now included a good professor and a bad professor. So now we're no longer in a reviewer and worker scenario, but instead we are in a scenario where we just have multiple agents and they're all going at it. Once again, from different perspectives, as you'll find out in a second. But we allow both of them to essentially to use the phrase that terminates the conversation. We ask the same question, so we're going to use 1 + 1 as our example once more. And the good professor will decide that 1 + 1 is very simply 2. But the bad professor says, well, it is clearly 3. And then says, I declare this problem solved. And because of the way we have set up our termination strategy, or rather the way we have implemented it down here, this terminated the conversation. This terminated our multi-agent system. So the bad agent, the unreliable agent, was actually able to say, we're done here, even though we weren't done. If we take the bad agent out, and we'll just run this again, you will find that, oh, sorry, my bad. That was the wrong time, or the wrong place to take out the bad agent. If we leave the bad agent in the group chat, but we take out the bad agent of the agents to which we apply the approval strategy or the termination strategy, then you'll find that even though the bad agent will, of course, keep saying this problem is solved, 1 + 1 is 3, we are not actually going to terminate the conversation until the good agent decides this is where we're done. Good. But we're not going to wait for them to discuss back and forth, because potentially this can take a little while. You can see here, is there anything else we want to consider? No, we're just going to cut them off now, because I want to move on to the next demo to make sure that Thomas also gets to show what he's been working on. And this is just to show you a different way of how we can do it, because it's great to rely on the LLM itself to figure out when it's done, but that also has shortcomings, obviously. So here I've built something slightly different. I've built something that actually has 3 agents this time. We have the good professor. We once again have the return of the bad professor. And then we have an assistant. And the assistant is not just an LLM like the other two. It has a nice little plugin that I call the experimentation plugin. So if this is your first time seeing semantic kernel, this might be a little confusing, but essentially we can write our own code to add into plugins that these agents can execute. I've made a little plugin here, or rather GitHub Copilot has made a little plugin for finding a prime number, and a little plugin for appending that number then to a file. Because what I'm asking these agents to do is to keep suggesting prime numbers. I want to find prime numbers. And most importantly, I want to make sure I know maybe when I designed the system that not everything that comes out of an LLM is actually true.
Mm-hmm.
So I wanted to make sure that I don't cut them off when they think they're done, but I cut them off when I have found at least 6 prime numbers. So we're using a deterministic strategy here. We're actually looking into that log file to figure out how many prime numbers have we actually found, and we won't terminate before, even though, you know, our bad professor is also pitching up with some, you could argue, dubious prime numbers, right? And we can see here, the good professor is starting off suggesting some numbers. The bad professor is suggesting some numbers. The assistant is running them, is actually executing that prime function and then logging them here to our experiment log. And this will, let's see, this is actually, would you like the next badge? Yes, please.
You really need to fire the bad professor.
The bad professor is really bad, right?
Yeah.
He just keeps on making bad suggestions as if he was prompted to do that. So the the assistant is verifying batches, and because I've instructed the professors to only provide a few examples each time, the conversation, of course, won't terminate immediately. Instead, we will just get a few suggestions every time, and then only when we've actually gotten all the way to 6 suggestions, the assistant or the conversation terminates. So this is another way of terminating a conversation, not based on what the LLMs and the agents actually say and what they have done in the conversation, or what they say in the conversation, but instead what they've actually done. So basing this based on the actual actions that were performed, the plugins that were executed. One last thing before I hand it back over, we'll just quickly switch back to the board here.
Good.
Yeah.
And maybe one important thing here.
Yeah.
As you also mentioned initially, everything that you wrote here in Python, you can do in C#.
100%. Yes.
So,
Yeah.
you're covered.
Exactly. You're covered. One thing I quickly wanted to mention is that, of course, in the example that you just saw, we had those 3 agents also just taking turns. They were just going around and around. If we wanted to implement something like what you see right now here, some kind of network structure, we don't just need to know when we're done and when to terminate, but we also need to know whose turn it is. And the same way there are termination strategies in semantic kernel, there are also selection strategies that we can utilize for figuring out when to actually select the next agent. And I've actually got the, hold on, here, I've got the documentation here. I'm not going to show you a demo because we don't have time for that, but I just want to quickly point out, you can apply the same principles for selecting a new agent. You can ask the agent, hey, who should go next, right? And then have that be, you know, the large language model that decides when to take a next action, or who to send it to, or you can have some other kind of pattern or even predefined order that you want to implement. With that said, I think I've been talking for long enough. Thomas, oh, sorry. I was not talking for long enough.
No.
I had another topic. Okay. I'll be quick about this one because this one actually doesn't have a demo. I just wanted to briefly talk about scaling this because, of course, we're going to run into situations where we have an agent and we start putting more things onto that agent. We start adding more tools, we start adding more data, the prompt is going to grow, and the conversation history is going to grow and grow, maybe even across lots of different topics. And obviously this is why, or this is another reason for why we might want to look at multi-agency. We talked about reflection being one of them, purely to scale out a system and to provide more, you could say, like customized tooling to each individual part of the system is another reason for why we might want to split a giant agent like this one into multiple smaller agents that can be run by different models, that can have access to different tools, that can also have different memory. We'll get to that in a second. And essentially, we can put them into tiers. We can have multiple agents report to some kind of supervisor agent, and we could scale that as much as we want to. Well, to some degree, we can scale it to as much as we want to with these layers. And if this reminds you of the way humans work together, then I think you're spot on, because essentially we make, large language models are trained on the way we communicate. So obviously they will also work kind of the way we as humans work together. So we can orchestrate them in that way as well. Think about the fact that, someone in the finance department in your organization probably doesn't know exactly what you were doing, and you don't know exactly what they're doing. But overall, the whole thing still kind of works out, right? And that's because we spread out responsibility. So the same way you kind of build organizations, you can also build multi-agent systems. So think about that maybe if you're thinking about how we can actually scale these systems when they start becoming more and more complex.
And you can say that this is also one of the key features of semantic kernel, right?
Yeah.
Being able to orchestrate, having multiple agents, having multiple tools inside the different agents,
having them communicate across multiple channels, right? That's something we haven't really mentioned. But of course, not all agents also need to be aware of the conversation history that's happening between someone else, and lots of interesting stuff. Good. Should we move on?
Yeah, let's do that.
Perfect, because I mentioned memory already. So now, there we go. Yes. Now let's actually talk about memory.
Yes. So you can say one thing that really defines us humans is the ability to have a memory. So it's based on our memory that we do different actions. It's the way we act. It's all based on what we have in our memory. Maybe I should take over here.
You want to take over? You're welcome to.
Yeah. Oh, no, you
Otherwise,
know what?
I can just move it for you.
That is so good. So you can say if we take like this totally classic setup of how a dialogue is going on, we see a person making a request. The request goes out to the different LLMs, and we get a feedback based on that. And all of that is really good. Issue is just that this is like one-shot copilots or the assistants, where the memory from session to session doesn't really exist. So if we want to add something on top of this, could be some information about who I am, something about my skill set, for example. If you take it a little bit to the right, you can see that is me. I'm 48 years old, I have a wife and 4 kids and all of that. And this is something that I would normally have put into the memory of an assistant that
you mean a human assistant as well?
Yeah, well, actually, yes. But also my AI assistant. And when we talk about memory, it's something that applies to both assistants, but definitely also agents. And when we take a look at agents, where especially the autonomous agents that runs and have longer execution time, being able to use a memory is really important. This is where they have the ability to self-reflect, they can self-improve, so they just not just execute on what it is that they get right away. So, oops. All right, let's take a look. So, yeah, so you can say in this case, we have different solutions available when we're talking about memory. And the more autonomous, the more advanced agents we are looking at, the more need and the more value we get out of a memory solution. We have some different ways we can do this. We can use, we have something called kernel memory that we can use. But we also have some abilities and features inside semantic kernel that we can use. It's called semantic memory search, and we can use that for putting data into a vector based storage. Could be different storage, different databases, could be local storage, etc. One good thing about beginning to storing thing in memory is not just that the agents can really leverage on this when they are running, but also all of the sudden we have a possibility to actually govern the dialogues that goes on in the agents. So that means that all of the sudden, because we begin to persist the memory, we can make sure that everything that goes on is in a good state.
It's a good idea to remember that govern is a word in the title of the session, right?
It is.
Yeah.
It is. Yes. But let's try to take a look at it.
Yeah, let's do it.
Let's see a demo here. So that would mean that I would need to present here.
Yep.
Just needs somehow this one too. Here we go.
Good. We're just switching over to.
Yes, perfect. So,
oh, we're not in VS Code anymore.
No, now we are in Visual Studio with a white theme and everything. Everything is good here, right?
And we're obviously no longer in Python either.
That's right. This is a good old C#. So, in this case, what I do, I have a bigger setup here. You'll have access to all of the source code for the demo here, so don't hesitate to dive into it. But we're using some different models from Azure OpenAI, both some chat models and some embedding models. In this demo, I'm also using what is called quadrant as my vector storage, and that'll be where I persist the data. Throughout the demo, you'll see that I will first persist some data in a news collection, and later on we will see that we persist some data in a user collection. So what I do here is I set up my semantic kernel. I add my Azure OpenAI chat completion service, my embedding generation service, and then I add quadrant vector store as a host, and then I add the two different collections that I will be needing. I then register some services, and down here, the most important thing is that what I do is I add my host service being chat service. If we take a look at that, it's actually quite simple. What it does when it starts up is that it starts loading some data. These data will be put into the first collection we saw before, so that every time we start up, it doesn't need to reload everything it has. And then we start a chat loop, so we can begin to do a chat with the user. When we do the loading of the data, you can see here, first of all, I make sure that the collection is created if it doesn't already exist. And then I fetch some data from 3 different blocks.
I like that you included the new Azure AI Foundry block.
Yeah,
that's very good.
Yeah. It's really nice, right? And what I do then is I simply go through all of the blocks, take it out, and what I do in the end is I add it to my news collection. Once that is done, I can begin to chat with it. So what goes on here is it says, well, we have created this plugin called text search, and we use that to enrich the data or the information we get from the different feeds. So what we does here is we invoke using semantic kernel. We invoke the prompt with our question in that the user has, and then make sure that using the plugin we get all of the data we need.
And I see you're also using streaming to make sure that you don't have to wait as long as you did in my demo.
Yes, exactly.
That's a really good tip. Yeah.
It shows something throughout the time. But it takes some time to load the data, I can say, though. But let's take a look how all of this looks. And you can say this is a really simple example, and most of all, this is more or less just a simple rack solution. You can see what it does here. It goes through all of the different feeds, reading them, making sure that if it doesn't already have persisted it before, it persisted now. All right, and then we are ready to ask it some questions. So we can say, any news about semantic kernel? And what you'll see is that it will find some different topics here. We have actually said only show the two most relevant stories, and it will show it including the link for the specific news. All of that really simple, really easy to go with. And if we take a look at my collections here in my vector database, you can see that here I have the collection news articles, and it has 29 items or points in it. In here, you can see what it is that we have loaded, including the link for the article itself. If we try to take this a step further and say, okay, let's actually try to benefit from us being able to use memory. So what we have added here is to say, okay, so every time we get a question from the user, we persist it. So what we do here is to say, okay, again, making sure that the collection is created, and then we summarize the user's question. That makes it really easy for us to, at a later stage, saying, okay, we have the queries, but we also have the summary. So that makes it easy to put into our chat services.
So you could say the interesting part of the memory here is not actually about remembering the blog posts. It's remembering what was being asked.
Exactly. Exactly. So not much have changed here. What we could do was to say, okay, let's delete the existing user queries. And if we try to run it again, did I change it? I changed it, right? Yeah, I changed it. We run it. Again, we load all of the items here. It's good that we shouldn't wait for this all the time. And here we can say any news about Azure AI Foundry, and ask that. Okay, so again, it shows me two different items. And if we try to go into our overview here, you can see that in my user queries, I've received the query that I asked here.
I love how your summary is longer than the actual question.
Yeah, it's really chatty, right? So the summary, the user is asking for update or news about Azure AI Foundry. So let's prompt it a little bit more, right? What can you tell me about Foundry, for example? Okay. And anything new going on for semantic kernel? Okay, so now I've asked 3 different questions. You can see here, they are in here. So what we can do now is to say, okay, let's actually benefit from us having persisted this. So if we say, okay, so what we do now is say every time the user gets in here, we actually try to predict what the user wants to ask about. And to be really fair, this is a really simple way to do a prediction, right? Because it's all relying on the LLM to do it. So what you can see here is what it does is it actually takes the top 5 of the user's queries, and based on that, it tries to using the chat service to say, okay, try to predict what the query would look like for the user.
But of course, nothing is stopping the smart people watching to just implement their better prediction function, right?
Yes, exactly. So this is a demonstration of how it could do, or the whole concept around it, right? So if we run it again now, what we'll see is that, again, loads the data. I should have skipped that in demo 3 here, right?
Yeah. Well, it's always good to remember.
Yes.
All of the cool news that are coming out and all the new updates, right?
Yeah, exactly. All right. So a little different thing you can see here is that it says type X and enter to get a predicted query. So let's try that. So here it says, okay, well, a possible thing that it would ask is, or what the user would ask is, what are the latest advancements in AI frameworks from Microsoft?
Yeah, because you asked about semantic kernel, right? And then you asked about AI Foundry?
Exactly.
That's a pretty good suggestion.
Yeah, it is. So again, really simple way to leverage on some of the memory that we persist. And the whole concept here is that if we put this into the systems that we are working on, where we actually try to be innovative about what we communicate with the user about, we can really get some cool solutions here, right?
Yeah.
Mm-hmm. Yeah. So as you can see, most of this was actually added by using different services within semantic kernel. Right now, there's not like this golden way to do memory and really leverage it. But hopefully this is something that will come at some point. Yeah, let's go back to our board.
Let's go back to our board.
Yes.
Let's do that. Maybe one thing before we round it off. I don't know if you have that on the right of your board. No, it's just demo time. Coming back to the title of our session, right? Mm-hmm. Agents that act and govern themselves. But you mentioned something. This is when Thomas and I were talking before the session. You mentioned that there's also an aspect here to governance from an outside perspective, right? That this allows us to actually govern the agents kind of from an external perspective because we see what's going on, right?
Exactly.
Memory for the agent, but also memory for for us to understand what's been happening, right?
Exactly. All of the sudden, we have a chance to really get an insight into, or a glimpse inside to what is going on behind the scenes when we have the autonomous agents going on.
And to maybe take it a step further, you could argue that in this example now, the user was saying, I would like a prediction, right? But imagine, apply this to the demo I shared earlier with the bad professor.
Yes.
Imagine if the other professor just remembers, hey, the bad professor is actually bad.
And cut him out.
We're not going to listen to him anymore, right?
Yes.
Or we're not going to ask him to provide their feedback. So there was lots of really, really interesting applications once we start going away from kind of the simple retrieval chatbots into more autonomous agents as well. So that's super relevant in that regard as well.
Definitely. Yeah. All right. So we are at a point now where we are at the Q&A.
Indeed, we are.
Yes, we are. So let's take a look to see if we have got any comments.
I've had a little bit of a look already. Hi to everybody who's saying hi. Hello back. Someone was asking in the beginning if there are C# versions of the demos that I showed. Exactly, perfect. And yes, so there are. They're not directly the demos I use, but they're the demos I base this on. So if you go to the semantic kernel GitHub repo, you can actually see that you'll first select the language you want. If you select C#, then you'll find underneath there a sample folder, and that one has the all of the different samples in C#, as well as in the other languages. Conversely, I was using the multi-agency sample from the Getting Started section there for Python, and the same is available in C# as well. Good.
Yep.
Then we also had a question of whether we're able to share the Miro.
Yes.
We weren't really planning to do that, but I suppose what we could do is maybe export that as a PDF and put that up in our GitHub repo where we're also sharing the sample code, right?
Yes.
We'll give that a try and upload that after the session. Speaking of, very good. Speaking of the code for the examples, you can find both Thomas's C# code and my Python demo code up there on GitHub. Good.
Yep. What did I say?
Then we've got a question. In the memory demo, are you loading the data into the context of the model before the user query, or can you extend it so that it requests for memory only when users need it? So in your particular demo,
yes.
Is it always looking into the previous history? I mean, in your case, the user is asking for when they want a prediction, right?
Yes, exactly. Yeah, so you can say, that should be like totally controllable. So yeah, definitely.
Yeah, and you could argue if, for example, we made that memory lookup something like a function that we just give to the agent as a plugin in semantic kernel, yes. It would then just determine itself when it needs memory. Right?
Exactly.
In your example, or in the example Thomas showed, that maybe isn't necessary. No. But if we worked in a scenario where, let's say, for example, Copilot remembers the name of your dog.
Yes.
Abby? Was that the name of the dog?
Exactly.
Or the wife? I've got to be careful. the dog. Those kind of scenarios, it would make sense, of course, to load that in on demand through something like a plugin rather than always having that in memory. Yeah. Then we've got a question from Derek here. Could you summarize how we can create similar agents and expose them as API endpoints? Then we don't need to keep all the agents in RAM, but we can use more distributed patterns. Yeah. So the question is, I mean, you're taking it to one place already, saying exposing them as API endpoints. I mean, that's one approach. It would be very interesting to see how, let's say, so far I haven't run into an issue where I was having too many agents especially given that we can split them out into hierarchies. We can have different channels, different streams where agents essentially operate independently. But if you do want to publish them or expose them, then you can essentially do this with, I would say, whatever method you prefer, right? Something like semantic kernel is incredibly open. You can just put whatever type of overhead or front end on top of that.
Yeah, you would definitely be able to do that.
Yeah.
Yep.
So use your preferred framework and put it on top of that. Then we've got a question here from AI for everyone. Like in 1+1 with both math professor and computer professor, when there is ambiguity, should the agent not use the user for clarification rather than given both answers? That's a great question. Because absolutely, in some scenarios, you might absolutely want that, right? In my case, I specifically prompted the math professor not to ask too many, or to not ask for consensus, but just to say, okay, I'm summarizing everything we've gotten here, and that worked for the demo. You might have a scenario where you would absolutely want to then reach out to the user and get their input and be like, hey, do you want a binary or do you want decimal? But I would say in a scenario like this, that would actually introduce more friction than to just provide both answers and let the user pick the one that they need. But it depends on the use case, and you could definitely prompt the agent to do either. Good. Then we've got a question here on rate limits. By having multiple agents, would that not increase the rate limit? Can we optimize the termination strategy so that the agents don't have the freedom to converse as much as they want? Really good question. Because absolutely, by introducing more agents, we are, of course, there's more conversation happening. We're calling the underlying language models with more tokens. We're using more tokens. We're using the AI models more. No doubt about that. Having multiple agents introduces an overhead. We can do a lot of things to make that more efficient. I don't know if you noticed this, but in my second demo, or when I guess my last demo, where I was sharing the example with the prime numbers, I specifically instructed, I didn't go over this. So if you notice this, it's because you have really sharp eyes, but I specifically prompted the agents to not waste time on chit chat and focus on the task, which made them actually just give the prime numbers, in some circumstances at least, just as a list. They would just be 2, 3, 5, rather than saying, oh, let me think of a few prime numbers for you, my good old colleague, right? The way they would talk in the earlier demos. Yeah. So, for conversation scenarios where there's no human involved, 2, 3, 5 is enough, right? We don't need all of the flourish. We don't need all of the decoration.
You also added a maximum number of times that it should.
That's right. The other thing, exactly. So I specified a cutoff at in my case 10 turns, and I said if you're not finishing within 10 turns, we're going to cut you off. Yes, and never run this without defining some sort of cutoff. I was once, and I can share this little battle story. I was defining my termination strategy, and I was just doing what I showed you in the beginning, where I was doing simple string matching, right? But to make sure that I can capture it regardless of how the AI model spells it, I'm turning the whole string lowercase. But then the string I wrote to match it up against actually had uppercase characters, so nothing would ever match it, right? So the agents would just keep talking, and they would figure out the solution, and then they'd be like, thank you very much, dear colleague. It's a great pleasure working with you. Oh, no, thank you. It's a great pleasure working with you. And they would continue doing that essentially until I run out of tokens. Yes, absolutely. Try to optimize your termination strategy, optimize your prompt. I mean, prompt engineering, even in the day of multi-agents, is still super relevant. So do that to limit the amount of tokens.
All right, final question.
Final question.
Yep.
What architectural patterns or tools work best to keep things scalable, responsive, and resilient when intelligence agents are reacting to real-time events at large? That's a big question.
Yes.
That is a really big question. And I suppose, do you have any immediate things that jump to mind?
Yeah, so you can say, so on the tool side, as you could also see here in the demos, we rely heavily on semantic kernel. This is really, you can say, a tool that makes it easy to get things done, easy to orchestrate your agents, and it is working really close with the AI extensions in .NET. So those two are like really good working together. So definitely semantic kernel is a good SDK to rely on.
Yeah, I think that is for a question as big as general as that is, and you don't need to be sorry. It's a good question. This was a good answer as well. So I think with that, thank you all for your great questions, and thank you for joining. We hope that you enjoyed the session. Maybe you learned something new. Maybe you got inspired as well to build some agents with some different multi-agent systems. And if you want to find Thomas and I on LinkedIn, you're more than welcome to follow us and reach out if you have any other questions after the session as well.
Yep.
So thank you guys very much, and have a great rest of your day.
Hi, everyone. Hope you enjoyed today's session. If you aren't registered for the AI Agents Hackathon yet, register now at aka.ms/agentshack and start hacking on the agent of your dreams.
And if you have any questions along the way, just post in our GitHub discussion forum or attend our live office hours in Discord. And of course, make sure that you keep attending the live streams to keep learning about agents.
Once your project is ready, submit it before April 30th at 11:59 p.m. PT to be eligible for our prizes. Thanks for joining.